Hi, I'm Ethan Fish, and this is my CA4 block diagrams. So first, we're going to start out with case 1. We're using a proportional gain controller to control a steering actuator. The actuator controls the vehicle and its lateral position, X of S. The desired lateral position, R of S, is the input of the controller. So here we have the block diagram located in the bottom of your screen. Damping ratio, undamped match frequency, and as well as the closed loop transfer function. So the closed loop transfer function was derived from this block diagram. We were given these values in the stated problem. We were able to solve for the transfer function, as you can see here, first bullet point. Now we'll go to the undamped transfer frequency for this block diagram in case 1. As you can see here, it's stated in this equation here. Then I go down to the damping ratio, which is also 1 over 2 times natural frequency, as you can see here. Then we wanted to run the roof criterion to see if this system is stable. And with this, we were able to determine that the system is stable for all positive K values. Then we got the step response graph for 4 different K values to kind of see what the system does, kind of get a stable system for our lane change. So it's a second order system. The undamped response is not ideal due to the vehicle position. Later position is oscillating around the reference point. Overdamped has a very high settling time. Really critically damped would be good if the settling time was the main criteria, but the controller would need to be modified due to uncertainties in the system and variations of the parameters. So with that, underdamped has a reasonable settling time and reasonable overshoot, so we will go with underdamped for our system. And here's some parameters that were set so we can find the stability in this system. The proportional constant can be designed based off any of the following criteria. Less than a 10% overshoot, a rise time between 2 and 3 seconds, and then obviously the undamped natural frequency has to be between 0 and 1. So here we have our stability graph for the underdamped system at K equals 2.75. It was deemed that 2.75 was best fit for the set parameters. So as you can see here, here's a step graph, step response graph, and then here's all the data that comes along with that, including the rise time, settling time, overshoot, peak time. We're also able to calculate damping ratio based on the first equation that I showed in the second or third slide, using that same equation with the 2.75 plugged in as for our K, as well as finding the undamped natural frequency, plugging in our K value into that equation to get our natural frequency. Like I said, the Roth criterion shows this system is stable for all the positive K values. So we were able to find the poles. There's 2 poles in this system at negative 0.5 plus or minus 0.5477 I. So there's one at plus and there's one at minus. So there's 2 poles. Now we'll find the steady state error for our K equals 2.75. And to find that, we will use this from our transfer function in system type 1. Step input is Kp goes to infinity, equals infinity, which will make our steady state error 0. Now we'll move on to case 2, where now an accelerometer is used to measure and compute the lateral position. Feedback is acceleration, not lateral position from the accelerometer. Lateral position must still be in the output, though, for the entire system. The acceleration signal is fed back to the accelerometer, and the accelerometer is modeled as a mass spring damper system. Then the output signal needs to be changed back to its position for comparing to the desired position. Okay, now we move on to the block diagram and closed loop transfer function. You can see here, kind of messed up here, there should be lines, arrows here. That's all right, you can see it. So we got this block diagram for our with our accelerometer that includes the accelerometer or the mass spring damper system. So with that information, we're able to compute this closed loop transfer function. This is the end result. There's computations that need to be done before this, but to save some time, I just wanted to give you the end result so you can see what we're working with here. Again, we did the root criterion of this transfer function to see if the system is stable, and which it was. Okay, now we have our step response with the acceleration of the accelerometer. It may look the same, but there's some data that shows it's not, and we'll get into that in the next slide. But here's just a quick overview of the step response for the accelerometer. Gives you rise time, same information. Now you can see we have 4 poles compared to the 2, and this is because we added the accelerometer, which is changing the system. Okay, now we'll go compare the data, and you can see the difference in the graphs. So case 1 will be the blue line, and case 2 will be the red. And over here you can see the changes that were done in the numbers behind this graph. So rise time in case 2 was decreased, which is good. So you can see that here with the red line, how it's more to the left. That slope is increased. So that's a benefit to this accelerometer. Settling time also decreased. So that's the time it makes it get to 1 here. So you can see red is below a little bit. The peak is a little bit higher, and then the peak time is substantially lower. Peak time is the peak here, time it takes to get to the peak. So there's the comparison of case 1 and case 2 with the accelerometer. Now we go into case 3, where we are going to modify the accelerometer parameters a little bit. So we're going to take that transfer function for the accelerometer here, it's HS. And the characteristic equation here kind of shows what these numbers are showing. So we have Wn, natural frequency is 10, and then the damping ratio of 1. We wanted to change our beta nu for this damping ratio, so we can change the damping ratio in here, which will end up modifying the transfer function, as you can see here. And then all in all, it changes the closed loop transfer function by a little bit on the denominator. Okay, now you can see that in the step response graph, as well as the data. And there, again, 4 poles still. All we did was modify that transfer function and the damping ratio. Now we're going to go in and compare all 3 of these. Trying to see the data. We're trying to get case 3 closer to case 1 because case 1 was what we would call the ideal system. So we want to get very close to case 1 with the accelerometer giving us that feedback that we want. As you can see, it gets closer to case 1 than case 2. Case 3 is kind of in the middle of all the data. So in here is the step response graph for case 1, 2, and 3, so you can kind of see the differences that happened when accelerometer was added, and then we modified that accelerometer a little bit. Thank you.